Thank you, everyone. Good morning. So we're going to be splitting this course, Trisha and I. I'll be giving the first lecture, and then she'll be giving the second lecture, and we'll kind of break up the third lecture. So today I'm going to be talking mostly about geometric vertex decomposability and sort of the story behind that property. So let's start with the field. It could be any field, actually. And an ideal inside polynomial ring. And we're also going to pick some monomial order. Okay, so last week, Fred introduced Gröbner bases, initial ideals. So let's just review that a little bit. And I'm going to use slightly different notation, right? So I'm going to say, recall that the initial ideal of I is just equal to the, is generated by the initial terms of the elements of the ideal. Okay, so I'll just mention here that last week we called this LT of I. Some people also call it, in of I, and so forth. So you'll see all these notations. Okay, and Gröbner bases, right? So what's a Gröbner basis? So G1 up to GS is a Gröbner basis. Of I with respect to the monomial order if this is just generated by the initial terms of the GIs. Is my writing too small for the people in the back? Okay. Okay, so what's the idea behind Gröbner degeneration? So the main approach is to simplify things by going to the monomial ideal setting, right? And we saw that with Sarah's talk when we talked about vertex decomposability, right? So the story is that we're going to use Gröbner degeneration to study properties of your ideal I. So R mod I, using properties of the initial ideal. Right, so the idea is you have some ideal, whatever complicated generators. If you pick your monomial order well enough, then maybe you'll get a really nice, square-free monomial ideal. If it's not square-free, then like Sarah said, you can use polarization to make it square-free. And you can sort of go to the square-free monomial setting and then study properties there. And the hope is that those properties kind of pull back to the, R mod I. And they do. And so like what properties? And so properties like reducedness, Cohen-Macaulay, so being Cohen-Macaulay. There's another property called Gorenstein. So if you can show that property using the initial ideal, then it's also true for the original ideal. And there's a whole list of properties, right? So we just kind of search like properties that are open in flat families. That's going to be, the setting that we have here. So why degeneration? There's this limiting process. We're not going to go to it today. It's That's a little bit technical, but what I'll say is that, I'll just write it here. So reference is going to be Eisenbud, chapter 15. And there it's going to describe, in what way this is a fat family and how to view these in a more connected way. Okay, any questions about this? Yep. Sorry, so commutative algebra with a view towards algebraic geometry. Yeah. And so one of the properties like you'll be proving on the problem set is, so you can check, for example, reduciveness, right? So if this is square free, then I is radical. Yes, that's kind of a quick property you can check right away once you're computing these initial ideals. Yes. Is that okay? Oh wait, this part done. Okay, great. Okay, so the property that I want to focus on, or the construction, is vertex decomposability. And then we're going to generalize to geometric vertex decomposability. So Sarah talked about this last week, and you hopefully did the exercise on her problem set. But I think it's worth just reviewing that and kind of going through an explicit example. Right, so let's call this vertex decomposability. Here I'll use her notation, not the delta. So we're using gamma for the Stanley-Reisner side last week, right? So simplicial complex gamma is vertex decomposable. If you have the following, right? So if, first of all, this is pure, right? So all the facets have the same dimension. So for the base cases, so either this is the empty simplex or just a simplex, a single simplex, or there exists some vertex V such that the link and deletion are vertex decomposable. Okay, so you've got this complex. You want to kind of break it up into nice pieces that are all, equidimensional, and you want to have a choice of vertex at every stage, so that you can kind of break it up in this way until you get down to the base cases. Okay, so let's go through an example. Okay, so let's say that we have this simplicial complex. Let's call this A, B, C, D, E. Okay, so what's the Stanley-Reisner ideal for this simplicial complex, right? So we're looking for all the non-faces. So you don't have, you have all the vertices here, A, B, C, D, E. So let's say this is in the ring with A, B, C, D, E. And you don't have the edge A, B, and A, E. And you don't have the edge B, D, and D, E. And then you can check that that's it. Okay, then there's these other simplicial complexes you can define in terms of this one, right? So one is going to be the link. And you have to choose a vertex. I'm going to start with the vertex A as my first choice, okay? So the link is supposed to be the set of faces such that when you take it with the union, so generated on vertices taken with the union with A gives you also a face of the original complex, right? So like CD is a face such that if you add the vertex A and generate that simplex, then it's inside the original simplicial complex, right? So in this case, the link is just going to be CD, and the deletion is going to be just, delete the vertex A. So any face that doesn't involve A at all. So it's going to be the simplicial complex. So D, C, E, and A. And when talking about vertex decomposability, there's also this other simplicial complex which comes up depending on what you're doing. So there's the star. And it's just going to be the cone from A to the link. Okay, so in this case, it's just going to be this. So I'm trying to view this vertex decomposability from the algebra side in terms of the ideals. So let's also write down the Stanley-Reisner ideals for these simplicial complexes. Right, so here, the deletion, what's it going to be generated by? So we don't have the AD and the BD. And now this is the issue that Sarah was mentioning, like if you include the, yep. Yes, thank you, and that's going to change the dinners. Yeah, so that's an issue. So if we view these as, let me say this. So let's start by viewing this viewed as complexes on the vertices A, B, D, sorry, A, B, C, D, and E. So if we do that, then we're going to have to throw in this this variable A here, right? And in a second, I'll do the version where we don't include that A. Right, so here we would have this ideal. Here we would have so what's missing from here? We would be missing A, B, and E. And here we're just missing B and E. So in terms of just this definition here, like, does this define a vertex decomposition? Can I continue the process with picture? Yeah. Yeah, let's do that. Right, so if you look over here, the issue is going to be the deletion, right? This is not pure, so we can't continue using this choice. Okay. I'm going to leave it as an exercise to show that this is actually not vertex decomposable. Right, so it's going to be one of the exercises. By symmetry, B, D, E will kind of give you a similar picture, and then you have to check the case C yourself to see what's going on there. Okay, so A is not a shedding vertex in this case, but what we do get is that I'm going to write the delta. So the Stanley-Reisner ideal for this complex is actually the intersection of two of the ideals here. So usually we talk about the link and deletion, but if you use the link and deletion, you intersect these two, you see that A's in both. So A is going to be in the intersection, which we don't want it to be because it's not, it's not in this ideal here. So we actually have to take the intersection of the deletion and the star. So you get this intersection here. Any questions up to this point? A vertex that gives you exactly, right. That's right. Yeah. So I should just do. Okay. If we instead view these as complexes where A is just, it's gone, right? So we've looked at the contraction of the rings so that we've eliminated the variable A. So let me say viewed on vertex set, no A now, so just B, C, D, and E. Then what would be the Stanley-Reisner ideals for the complexes here, right? Well, this one's defined in terms of A, so I can't do it in this setting, but the link and the deletion I can, right? So then you would get that the I link of A is equal to just the B and the E. And you would get that the deletion is just BD and DE. Yep. And now the intersection over here is going to change slightly, right? Because this one involves, the variable A, and then these other two don't. So you have to sort of throw it into one of the ideals that you're intersecting. So it's going to be the link intersect the deletion, but you're going to add in the variable. So if I'm doing this generally, so just XV, I guess. Sorry, that's a bit messy. Let me rewrite it over here instead. This here. Here, I'm just saying for general V now. Yeah. Yeah. Okay, so why was I writing down these ideals is because we want to be able to do vertex decomposability from just the ideal without having to draw the pictures all the time, right? So how do we do that? So if you kind of just stare at the ideals and look at the process, you might notice the following, right? So let's say if we write our ideal as H1 up to HL. Okay, so here we're going to say XV doesn't divide the QIs or the HIs. Okay, so basically it's going to be the monomials involving the XV, and it's going to be monomials that don't involve XV at all. Okay. Then how do we write the link and the deletion in this case? Right, so you notice over here that the link was just BE, which are the, I wrote it A first, but the coefficients of the terms involving A, right? And you also have to actually throw in everything that doesn't involve A. So this is actually going to just be Q1 up to QK, and then all the H's. And what about the deletion? How do you get from here to there? It's just going to be the h's. Yeah, exactly. Right, so it's just going to be the stuff that doesn't actually involve the variable xv. So just the h's. Like this. Okay. So if someone says, is this simplicial or complex vertex decomposable, you can just write down the ideal and kind of do this process and just check. So for the purity, you're just checking that these are unmixed on the ideal side of things. Any questions? Yep.
Sorry, if we use this formula with based on Shell, in our example, would it I delete it to
Yeah, so this is viewed as complexes with the variable a still there. Yeah, you need to work on the contraction. Yeah. Okay, so one reason why I'm writing those out is because the generalization to geometric vertex decomposability will look very similar to this story, right? So geometric vertex decomposition. So now we're going to be working with any ideal, not just a square-free monomial ideal. Yep.
All right, I think I'm still not clear on how you go for compatibility with what you did. You said the example of the bow tie isn't vertex decomposable?
It isn't, that's right.
It isn't. So this decomposition of the ideal, like, you have to do such a composition like for each thing in the intersection, and if that terminates, then it's vertex decomposable. I'm still unclear on that.
You need to check that it's pure at every step. On the ideal side, that means unmixed. So here, the deletion is the intersection of D and this, right? So one has height 1, height 2, so it's mixed. So this would not be a good choice for vertex decomposition. So like what you're seeing here in terms of the picture of like you have different dimension components, you can see on the ideal side, and that's what you're checking there. So the game you're playing here is like choose the vertices such that the ideals that you get at every step are unmixed.
So you're decomposing the ideal into the intersection of things, and each time you choose a vertex so that the way that you split it, you hopefully get equidimensional things at every step. And eventually, if you could do that,
yes,
you have an intersection of a bunch of things with the same dimensions, then it is the vertex decomposable.
If at every step, so it's like you've got the link and deletion, and you're going to continue the process link and deletion for that, link and deletion for that. Every one of those ideals has to be unmixed. Yeah. If you could choose a vertex such that that works. Yeah. So the hard part is choosing the sequence usually. Yeah.
An example of one that is vertex decomposable?
The one that, so we'll go through an example, but yes, the one that Sarah mentioned last time, just the path of length 3. Yeah, exactly. So we'll come to that. Although I should probably go a little faster. So, okay, so what's the general setup here? We're going to just look at Lex orders now to make life a little bit easier. So assume that this is a Lex order where the greatest variable we're just going to call y. So yeah, some Lex order, whatever the the largest variable is, that we're going to call that y. And we're going to write the Gröbner basis of y that we started with as, let's see. So y to the d1 q1 plus r1 up to y to the dk qk plus rk, and then all your h1s again. And we're going to take the di to be greater than 0, and y doesn't divide any term of the QIs or the HIs. And the initial Y form of this is equal to this. So what I'm saying is you write out you view this as like this polynomial in Y, and all the stuff that has the highest power of Y, right? So all the monomials that have the highest power of Y, those are going to be part of your initial Y form, right? So that's what I mean by writing it this way. And so I'll just do a quick example to make sure we understand what's going on here. So like, what's the initial Y form of x squared Y plus CY plus W cubed? Right, so the highest power of Y is going to be just Y to the 1. Which terms have Y to the 1 in them? It's just going to be this and this. All right, so it's going to be x squared plus Z times Y. And this is going to be your QI. In particular, the initial Y form don't have to be monomials, right? So it's not like the initial term where you get this monomial. You can get a bunch of things for the initial Y form. If nothing involves Y, then the initial Y form is everything. It's just the polynomial itself. Yes? Sorry, so just a lexicographic order, so you have an ordering of the variables, and I'm just saying Y is whatever the largest one is in that lex order. Like I'm calling Y specifically because I need to use the Y for the decomposition. Right, so it's like if you have some order, like this, then I'm calling this my Y, is what I'm saying. Yeah. Okay, so using this, we're going to define two ideals, just like we had two ideals over there. We're going to call them just the C ideal and the N ideal. And it's just what I wrote there, right? So this has been set up, so this is just going to be the QIs together with all the H's. And then this is just going to be all of those elements that don't involve Y. Okay, so it's going to be an exercise to define this a little more intrinsically. You can define this as a colon ideal. And this, you can see that well, I'll just write down the statements, but you're going to prove this in the exercises, right? So you can also show that this is just equal to initial Y forms of I, and then colon out like all the powers of Y. You can also check that this is true for the N ideal. So this is equal to this. Okay, so once we have that, then we can talk about, actually landed on the same board. That's good. So I is geometrically vertex decomposable, and I'm going to abbreviate this as GVD. I know Megumi doesn't like when I use the acronym, so I hope you'll forgive me. So we're just going to call it GVD, and sometimes we also refer to like an actual decomposition as a GVD, so we're kind of abusing notation a little bit. But I is geometrically vertex decomposable if I is unmixed. And we need that we have the decomposition that we had there in terms of the intersections. So it should be CYI intersect this. Okay. And the contractions of this and this to the polynomial ring where you remove the y. Or also GPD there. You also need base cases, right? Right, so like you want to keep doing this until you get down to what? Well, you can get down to the zero ideal, the unit ideal, or just an ideal of indeterminates, right? So like xi1 up to xij, where j can just run from 1 to, what was I doing, n? Yeah. Okay. So let's try a very simple example, just ab minus c squared inside so if you try the Lex order a greater than b greater than c, so you're using this as your y, right? Then what are each of the ideals, right? So c, ai, and nai. Right? So you say, okay, well, here's my a. So the qi is just going to be the coefficient of that a, so just the b. And then I'm supposed to throw in all the HIs, but there's no HIs because there's just one generator. So it's just B. And here's supposed to be all the HIs. There's no HIs because there's just one generator, so it's just 0. Right? And you can check that. So maybe I should also write down, like, what is the initial A form of I? It's just going to be the whole term AB. And here you can check that the intersection works, right? This is equal to the intersection of this and this plus the ideal A. If instead you took that Lex order, so if I start with a C instead, right, then what's going to happen? So here we just want the coefficient. In this case, it's just a unit, right? So this is just going to be the unit ideal. Again, we get 0 for the n ideal. And now here, this doesn't quite work out, right? So if you take this intersected with this plus the ideal C, you don't get, well, I didn't write it down, you don't get C squared, right? So in this case, it's not true that this gives you the correct intersection. C intersects n plus y. So by the way, when you get this situation here where the C ideal is just a unit ideal, or There's another situation where the radical of C is the same as the radical of N. Those are called degenerate GBDs. Otherwise, it's called non-degenerate. You'll need that for the exercises, so I should just mention it here. Yes.
So being, are you fixing one thing for all Lex order and then testing whether something is GBD back to that Lex order, or do you get to pick the Lex order?
Okay, so the nice case is you have a fixed Lex order and you just use that at every step. And then you get some extra nice properties there. The definition doesn't require it. It just requires that the N and C be GVD in the contracted ring, so you can actually change the order as you go along.
Okay.
Yeah.
And also, any reason why C and N?
Oh,
My fault.
she wrote the
We'll
paper.
take it first. It's late, and the legion.
Just to clarify, Sergio.
Yeah.
So you can take the lefts, like the ordering of the variables at each step.
That's correct.
Okay.
So there's going to be examples where you, and there'll be one of the exercises where you need to do that.
I see.
Yes.
What was the special other thing that you said that we were doing in the exercise?
Degenerate and non-degenerate. So GVD is degenerate if either the C ideal is just the unit, it's just this, or this. So this is, you just saw an example of this. One of the cases where this happens is if Y doesn't appear at all in the reduced Gröbner basis. There's other cases too, but
And then
Yeah.
the C inside the radical of this, and
that's right.
that's the C from the CYI.
Yes. So this example is just to show you that it looks like you should have like, the variable, the generators are square free in the variable you're using in the Y. And that turns out to be true, right? So this is going to happen. So this is going to happen if and only if I is square free in Y. It just means that you have a generating set where Y appears to power 1 everywhere. So I should mention, sorry, a little bit of history where I talked about geometric vertex decomposability. So it was first introduced by Knudsen, Miller, Young. They were studying Schubert varieties. And then later, the definition that you see now was given by Jenna Ratchcott and Patricia Klein. And they show this connection to liaison theory. So Tricia will be highlighting a little bit more of that linkage story in her talk. So this tells us that this intersection is actually not that, like, you can tell very easily whether this intersection happens. You're just looking if Y is square free. If it's not square free, then you can't get this intersection. You can't choose it as a variable for your GBD. Okay. There's also a theorem that tells you that if I is GBD, then it is radical. And furthermore, if I is homogeneous, it's also homogeneous. Then R mod I is Cohen-Macaulay. Okay, so you get the Cohen-Macaulay property, just like you did with the vertex decomposability in the simplicial complex setting. Okay. You also get Glitchy, for anyone who knows anything about liaison theory. Okay, so we're not going to go into that, but you get some other properties too. Okay, so what I need to do now with the last 10 minutes is, let's see, is talk about that really nice case So the question was, do I have to use the same Lex order throughout? And the answer was no, but in the case that you do use Lex order throughout, then there's some nice properties. So I'm going to show you now what happens in that situation. Okay, so okay, so let's look at an ideal I generated. So I'm just going to show this with an example. So I generated by the 2x2 minors of the following matrix, so just a 2x3 matrix. Let's just choose this ordering here. We kind of go from right to left along the rows and then upwards. So 2, 2, 2, 1, 1, 2, 1, 1. So the 2x2 minors end up being a Gröbner basis. So what this is doing is picking out the diagonal terms, right? So like for this 2x2 minor, the initial term is going to be the x11, x22. And then you have the x11, x23. And then you have the x12, x23. Okay. This is the Stanley-Reisner ideal of the simplicial complex you saw last week from Sarah's lecture, right? So let's talk about the vertex decomposability of that. And then let's compare it to a GVD for the original ideal. Okay. So on one side, you've got this simplicial complex, x11, x12, 22, and 23. And if you did the example last week, then if we start with that variable, so just following that order, then the link is just going to be this x22 by itself, right? And then what's the Stanley-Reisner for that? Well, it's going to be everything that's missing in the contracted ring. So there's no more x23, but there still is the x11 and the x22. So x11, x12. And the deletion is going to be just this one. Two, three. There we go. Okay, so again, you can just see this algebraically, right? So here you're just taking out the coefficients of the x23, right? So here's the x23, coefficient x12, x11. You also throw this in, but it's a multiple of those. And then for this one, you just delete anything involving the x23. That's just the first term here. Yep. Yep.
Ideal of the deletion of x11, comma, x2.
Product, yeah. Okay, next in our order, we use x22. Right, so then you're going to have, again, the deletion and the link. So here, this is going to be, so this is the vertex that we're using. So the link is going to be the x12. Here you just get this. The deletion is just 0. Okay, this is vertex decomposable because you just got down to the simplex case. or the, yeah. Okay, so there's the 2x2 minors. So let's try a GVD for this with the same order. Right, so we're going to start with the x23, and we're going to have the C ideal and the N ideal with the variable 2, 3. So what's the C ideal here? So again, here's the x23, here's x23. So the coefficients x12 and x11. You also have to throw in this generator, but it happens to be a multiple of those two, so I'm not going to write it down. And then the N ideal is going to be any of these generators that don't involve the x23 at all, right? So this doesn't involve x2, sorry, these two involve x23. This is the only one that doesn't. So here the ideal is just going to be x11, x22 minus x12, x23. This is already GVD because it's just an ideal of indeterminates. This one we have to continue, right? So the next variable in the order was the x22. So here it is. Its coefficient is the x11. There are no generators that involve the x22. So this is just going to be the 0 ideal. Life is good. We're in the base case for each of them. I have to check unmixed, but everything's unmixed. So just check that at every step. Okay. And you've probably noticed what the relationship is with the picture here and the picture there. I mean, first of all, the diagrams look similar, right? And you have that the initial ideal here. So you can degenerate this to, you know, that ideal there. And then this one, it's going to be messy, but this one generates to that. And the initial ideal of this is going to be that. And the initial ideal of that is that, and so forth. And that's going to be true in general. Okay, when you have this Lex compatible GVD. So on one hand, you can just degenerate to the square free monomial case, do the vertex decomposition there, and show that it's vertex decomposable. On the other hand, you can just do a GVD here, and it corresponds to each of the pieces you would have done in the vertex decomposition, as long as you're using the same order thread. Yes. It just means that you're using the same, so you're using a Lex order and you're using it throughout for every choice of, yeah, you're not changing things as you go along. So on this side, you have that this is vertex decomposable, right? Which implies that R mod I is Cohen-Macaulay. And then because of that, with Gröbner degeneration, being Cohen-Macaulay is open in flat families. So if it's Cohen-Macaulay here, then it's also Cohen-Macaulay there, right? You also get square free, so I know that this ideal is radical, right? So you can kind of view things from the perspective of I degenerated, I check the properties here, and then it's also now true of the original one. On the other hand, we also have the theorem that tells us, oh, this is GVD, it's homogeneous, it's Cohen-Macaulay, and it's also radical from the theorem too. Okay, so you can get the story on both sides. But again, you'll see an example where like you have to work on this side and not that side because there is no square free degeneration. Do I have maybe one more minute? Okay. So I just want to mention very, very quickly. So first of all, you can compute this on Macaulay too, thanks to Adam and Mike in the back. So they have a package, geometric decomposability, which you can just write your ideal out, is GVD, and it'll tell you if it's GVD and kind of spits out the orders that work and all that. Okay, so you can check this by computer because it gets messy pretty quickly. The other thing that I want to say, so I'm not being precise here, but I just want to say that the height, the regularity, the multiplicity, the A invariant, which is related to the Hilbert, like the degree of the Hilbert polynomial, can all be computed in terms of the C and N IDs. I'm not being precise here, but what I'm saying is that if you have this GVD and you have the C and the N at every stage, you can write the regularity in terms of the regularity for C and the regularity for N. You can write the multiplicity in terms of regularity, like very explicitly, right? Like this, I'm not going to write on the formulas. It's in Jenna, Adam, and Ty Nguyen's paper on the 3 invariants of geometric vertex decomposability. Same thing with height, like height of I is equal to height of C is equal to height of N plus 1 in the non-degenerate case. Degenerate, you have to take care of some issues, but the point is that you can recursively compute all these things. So why GVD? Why is it important? Because you can break things down really nicely and get all those properties like in a recursive way. Okay, I think I've gone over time. Sorry.